Now we want to see how we use vector functions to model projectile motion. So we have lots of situations where we have an object that is launched, shot, thrown, whatever, with an initial speed from a particular height and at a known angle. So let's see how we can incorporate those quantities into a vector function, starting with the only force acting on the object once it is released, and that's the force of gravity. Now, since gravity is acting downward, we will choose a vector function that has a negative g as its second component. Now we're just using g for the acceleration of gravity. The number depends on whether we're using feet and inches or whether we're using meters, centimeters, and that sort of thing. So if we do the integral of the acceleration function, we get the velocity function. And notice that in our velocity function, we have a constant of integration, capital bold C, which means some vector function. We will call that vector function V0, the initial velocity vector. So here's our velocity function from the acceleration function. If we integrate that, we get our position function, again with some constant of integration, which is a vector, which we will call the initial position vector, R, capital bold sub-0, the initial position vector. So this is our ideas that give us our initial position, or our position vector. Now we'll clear up and specify some of the notation. Notice here I'm using the quantity V0 to represent the magnitude of the vector V0. So the vector V0 is the magnitude of V0 times the cosine of the angle, and the magnitude of V0 times the sine of the angle. Well, the magnitude of V0 we're just calling V0. So we will use that for our V0 vector and do something similar for our position vector. How do we describe the position vector for this? Well, we will assume a y-axis that goes right through the object, and so the initial position vector would be a 0, h. And so this would be what we get when we substitute that in. Now we're going to multiply through by the t to have just 3 vectors that we will then add together component-wise to come up with this. Now this is our position vector for any situation involving projectile motion. Here's a sample problem you can read about in your book. They use this as an example, and we've got a cannonball that's fired from a 100-foot cliff. The initial speed is 100 feet per second, and it's at an angle of 30 degrees. So let's write the position function. From the generic position function that we just developed, we can substitute our values and then simplify to get the position function for this problem. And from that, we should be able to answer questions such as the maximum height of the cannonball. Well, the maximum height of the cannonball, notice, is nothing more than the vertical component. The vertical component needs to be maximized. Now, if you remember your Calculus 1, you maximize that by doing the derivative setting it equal to 0, and then solving. Now the value of t is not what we're looking for, but that is the value that gives us our maximum height. So we want to substitute that back into the y component of the position function. Now likewise, if we want to find the length of time until the cannonball strikes the ground, we simply recognize that when the cannonball strikes the ground, then the y component is 0. So we need to take the y component and set it equal to 0. Solving the quadratic equation, we actually get two answers. The negative answer obviously has no meaning in this situation, so it's got to be just the positive answer. The length of time, 19.08 seconds until the cannonball strikes the ground. Now to find the distance away that the cannonball strikes the ground, we already know the time of flight until the cannonball strikes the ground. We simply notice that the distance away is nothing more than the horizontal component. And so we plug in to the horizontal component, the 19.08.